In this slice of physics, we want to discuss the definition of the electric potential energy due to an electric field. So we're going to consider first a parallel plate, which produces a uniform electric field. So let's consider then a parallel plate capacitor. So I'll draw two plates. I'll let one plate be a positive side, let this be positive, and this side to be negative. And I'll place a positive test charge between the plates. And we know that there is an electric field between the plates which is uniform, so I'm just going to draw a few of them. And it points from the positive plate to the negative plate. So here is the electric field. So we know that there is now a force on this positive test charge in the direction of the electric field. So here is the force. And we know therefore there is an acceleration in this direction. So the object will accelerate toward the negative plate, gaining velocity. So if I start here at some initial velocity of say 0, and let's say we will finally reach a point here, a new point. So at this point here, I have some initial position, and at this point here, I have some final velocity at some final position. We could determine the final velocity simply using the concept of a force. So if we use the force model, so I'm looking at the force model, acceleration would be q e over the mass of the charge. So the final velocity would be final from our kinematic equation squared would be the initial velocity squared plus 2 times the acceleration times the separation, the displacement from the initial position to the final position. So if I do that, then I get V final squared is V naught squared plus 2 QE over M times the displacement. Now I can rearrange this expression, putting the velocities all to one side, and we would arrive at, I'll do my algebra, I would find on this side this expression. And what do we notice from our early discussions? The left-hand side, this side, represents the change in the kinetic energy, and this side represents the work. Which is work done by the electric field, which is Q, the test value of the test charge, the value of the strength of the electric field, times the displacement. And if you recall from our discussion of energy, this work done by the electric field will be defined to be the change in the electric potential energy the system being consistent with the test charge and the electric field. So the system here is the parallel plates and the charge make up the system. So we arrived at the concept of the electric potential energy for a uniform electric field from the idea of the force model, that if I have a positive charge sitting in an electric field, it will move in the direction of the force, acceleration. So we can think of the electric field here between the plates, that there is a change in potential energy, and it's moving from a high potential energy to a low potential energy. So let me redraw the parallel plate. So redraw it. So here's the positive charge. Here's the negative charge plate. So we can visualize at this point at x naught, this represents a place of high potential energy, and x final represents a region of low potential energy. So the charge will move, the positive charge will move from the high to the low. This is an analogy to free fall. If you think about free fall, if I have a ball here, a certain initial height above the ground, and it's going to fall to this position, say y final. It starts at a high potential energy due to gravity. This will be the high region. It falls to a low, gaining kinetic energy. So we can now define electric potential energy for a uniform electric field. The change in the electric potential energy will be Q E, the intensity or the strength of the electric field, times the displacement in the field. So let's look at a few examples so we can understand this equation some more. So here's an example. You're given the strength of the electric field, you're given the displacement, you're given the test charge, and we just want to find the change in the electric potential energy. With the change in the electric potential energy, U sub V, is equal to the value of the charge, Q, strength of the electric field, and the displacement. So Q is 1 nanocoulomb. The strength of the electric field is 2,000 newtons per coulomb. Times the displacement, which is 1 meter. So our change in the electric potential energy is 2 times 10 to the minus 4 joules. In the next example, let's say we're given the change in the electric potential energy to be 100 joules. The displacement is 1 meter, and the test charge has a value of 2 coulombs. What is the strength of the electric field? change in the potential energy is the charge, the value of the charge, times the strength of the electric field, times the displacement. So E, the strength of the electric field, would be the change in the electric potential energy over Q times the displacement. And we find that our electric field intensity is equal to 50 newtons per coulomb. And here, our final example, I'm going to have two parallel plate capacitors. I'm going to release a charge Q, a positive charge Q at position XB, and I want to know what is its velocity when it reaches x of a. In other words, what is the final velocity given some initial velocity. So let's say we're given the charge to be 1 coulomb, the strength of the electric field to be 200,000 newtons per coulomb, and the mass of the charge is 1 times 10 to the minus 3 kilograms. And we'll start the initial position, x of b, before I release it at 0 meters. And I want to find it when it reaches 1 meter. And since I'm going to release it from rest, I'll have initial velocity, or the velocity before, to be 0 meters per second. So I'm interested in finding the final velocity, or the velocity at point A. So I'm going to be using the work energy principle, and that is the change in the kinetic energy will equal to the work done by the electric field. Or in this case, this will be the change in the potential energy, negative. And this side will be minus QE times the displacement. And the side over here will be the change in the kinetic energy. Actually, this is positive, not negative, sorry. And so I can see here then I have here the change in the potential energy is equal to the change in the kinetic energy. So if I do my algebra, then since V sub b is 0, I would have 1/2 mVb 0, but I have 1/2 mv squared A is equal to the change in the potential energy. So V sub A squared is 2QE times the change, its displacement over its mass. And I find that the velocity at position A is 20,000 meters per second. And to summarize, what we have found is the electric potential energy for a uniform electric field is simply given by the value of the charge in the electric field times the strength of the electric field times the location, and I'm picking the location here reference to the negative plate. And also to remember, for a parallel plate capacitor, the strength of the electric field is given by the charge on the plate divided by the area divided by the permittivity constant of free space.